Ni hao. Hello. This is the 25th lesson in heat transfer. In lesson 25, we will begin the final unit of heat transfer on thermal radiation heat transfer. I am excited to begin this particular unit because I find thermal radiation heat transfer to be the most exciting of the three modes of heat transfer. In the first part of lesson 25, we will review material from earlier in the course and discuss again the mechanism associated with thermal radiation heat transfer. In addition to viewing this part of the lesson, you may wish to go back and watch the earlier lesson on thermal radiation heat transfer. By the end of this part of the lesson, you should be able to list which parts of the electromagnetic spectrum are attributed to thermal radiation heat transfer. You should also be able to explain in your own words why thermal radiation is emitted from matter. On with the lesson.
So as a reminder, the mechanism for radiation heat transfer is electromagnetic waves, or equivalently, because we have this dual theory of understanding radiation, transport by photons. Okay, photons are the particle that we attribute to electromagnetic radiation. And the distinguishing feature of radiation heat transfer in comparison to conduction and convection is that radiation will occur through a vacuum. So there's no intervening matter required. We don't have to have molecules touching each other in order to achieve radiation heat transfer. That is most definitely the case in conduction and convection. Okay? So conduction, we need in gases and liquids that random walk and molecular collision. We actually need the matter to move around and collide. For convection, we have that plus the bulk motion of those molecules. Like, it's all about the matter. Radiation is not all about the matter. It's about the photons, and the photons can move through space. Right? It's a good thing that happens, because we wouldn't be alive if that wasn't the case, because we get all of our energy on this planet from the sun, and that energy is transported by radiation through the vacuum of space. So you don't need to have matter. If you can think back to the beginning of the class, I had you watch a YouTube video about the mechanism of where photons come from. And you can go back and look at it to remind yourself. But I think for me, the picture that's best is, I imagine if you ever played popcorn as a kid, you got a big parachute or a big blanket, right? You stood at the edge and shook it, right? And you made balls pop up and down from the shaking of that. Anybody do that? I think if you think about the balls as electrons in matter, and the shaking of that surface is like the energy states, and kind of the way that the electrons are getting jostled around from the temperature of matter, right? Because matter is at the molecular level always moving around. And so that's kind of like the shaking at the end, right? You've got temperature, and so there's this thermal energy, this it's microscopic kinetic energy, and it's causing the electrons to jostle around. And when you pop a ball up high, that's like an electron getting kicked up from a low energy state to a higher energy state. That only happens when you have an emission of a photon. When it comes back down, right, it has to give up that energy, and so a photon gets spit out. So it's that, if you imagine the electrons as playing like popcorn, right? When they come back down, they emit photons. They emit photons. Every single time an electron comes back down, it emits a photon. And how much it comes back down is related to the energy of the photon that comes out, which is related to the wavelength of the radiation. So the shorter the wavelength, the higher the energy of the photon, the bigger the drop in the electron energy level. So over here, we have weak photons, all right? So small energy transitions. And on the right-hand side, short wavelengths, we have high energy photons, or short wavelengths, or large energy gap changes. that make sense? Now, there is kind of a, because of the nature of matter and the nature of the energy states of electrons, when we say thermal radiation, what we really mean by thermal radiation is the photons that are emitted because of this temperature effect. It's a natural process. It's just always happening. We don't have to do anything special to get these photons to come out. Photons are coming out of my skin, my jacket, the floor, the table, everything, right? Anything that has a temperature is emitting photons. But the photons associated with that emission tend to be restricted to this range of wavelengths, which is why we call this the thermal radiation spectrum, okay? It's not that there aren't shorter wavelengths or longer wavelengths, okay? Microwaves exist. But the way that your microwave works, you don't just, right, you have to push start and energy gets drawn out of the wall, right? Like you don't put your coffee in, shut the door, and then walk away, not doing anything, right? And you open the door up and it's hot again, right? You have to actually have to push start and the microwave does something. It takes the electricity from the wall and it uses it to excite an emitter, which is like an artificial, an excited thing that causes the microwaves to come out. That doesn't happen on its own, right? You're doing something extra. And you can think of the same thing like you hear about nuclear decay of material and nuclear emission. So those photons are being emitted because of a different type of process than the temperature of uranium, right? It's, you know, we're getting gamma rays come out because of nuclear decay, not because of the temperature of the uranium, right? Like the uranium has some temperature, but you're not getting gamma ray radiation because of its temperature. You're getting gamma ray radiation because you have a change in the isotope, right? So does that make sense? So that's why we kind of restrict it to thermal radiation is at this tighter range of wavelengths from the long IR to the short or to the long UV.